The virtual particles refer to matter and antimatter particles coming to life.
Correct.
Can we just talk about the antimatter part of that? So it's starting with Paul Dirac, one of the most legendary examples of math leading to physics. So the math suggesting that so something like an antimatter should exist, and Paul Dirac taking it seriously, and then eventually showing that it does exist. So what evidence do we have for antimatter?
So antimatter was predicted in 1928. Paul Dirac was trying to merge quantum mechanics and relativity because the original Schrödinger equation was not relativistic. And in doing so, the equations were complex, but in the end, it came down to something like equation squared equals 1. You take the square root of both sides, you get equation equals +1 or -1. +1 was the electron, -1 was something. You didn't know what it was. There was some conversation for a while, thought maybe it might be the proton, but that didn't seem to work out. And so he insisted that his equations were right and that there was an antimatter. He didn't call it an antimatter, but a positively charged sibling of the electron, what we now call the positron, the antimatter electron. So it was predicted. It was discovered in 1932 by Carl Anderson and his student Seth Nettermeyer. They saw an antimatter electron, and that was pretty cool. So that right there, they knew it was real. Antimatter was predicted. It was observed. That's that. In 1956, the antimatter proton was created, and that required a large particle accelerator, high enough energy to make it, and that was done at Berkeley. And a year later, the antimatter neutron was discovered. So at this point, and now jumping ahead to now, we can make, using energy by smashing particles together, we can make antimatter protons. We can make antimatter electrons. We have gone so far to make antimatter helium nuclei. So we have made 2 antiprotons and 2 antineutrons, combined them together to make an antimatter helium nuclei. This has been done, been observed, no question. At CERN, they have gone so far as to make antimatter hydrogen. They take a beam off one of their lower energy accelerators. They make antimatter protons. They collect them. They slow them down. They cool them to almost absolute zero. They take sodium-22, which makes antimatter electrons. They slow them down. They bring them together. They coalesce them, and they make literal antimatter hydrogen atoms with an antimatter proton surrounded by an antimatter electron. And they have done incredible measurements. They have agitated the atoms and caused it to emit light. They have looked at the light that comes out of antimatter atoms. And the question is does the light coming out of antimatter hydrogen atoms have exactly the same spectral characteristics as ordinary hydrogen, which we predict that it does? And the answer is it does. So the tests have been staggering. We now know a great deal about antimatter hydrogen. Recently, like 2023, I believe it was, one of the experiments called Alpha at CERN made antimatter hydrogen, put it in a bottle, and released it and watched which way it would go. Did it fall up or did it fall down? Because while it kind of makes sense maybe to think that maybe antimatter falls up in the same way that we have Coulomb's law, you've got electric charges and they might attract or repel. However, there was lots of ample theoretical reasons to believe that antimatter also would fall down. So they did this fantastic measurement, and they put in hydrogen. And they calculated that if they did this, something like 80% of the hydrogen atoms would fall through the bottom of the bottle, and 20% would go through the top, just because gravity is very weak and the atoms will escape wherever they do, but there will be a bias pulling hydrogen atoms down. So they did exactly the same thing. And what did they find? They find that antimatter falls down. Now, they do not have a good enough measurement at this time to say that the gravity that antimatter experiences is 100% that of matter. What they have measured is that antimatter fell down with 75% the strength of regular matter, but there were big uncertainties. There was plus or minus 0.13 due to the experiment, which was good but imperfect, and plus or minus 0.16 due to their theoretical model. So it's like 0.75 plus or minus something like 0.29. And that means there's a good chance it's between 0.5 and 1, which means it's consistent with 1. So they are improving their measurements.
Well, if I can, I would love to take a bit of a tangent on that topic because I went down a rabbit hole watching some of your videos on antimatter. And I mean, Fermilab was the hub for the production of antimatter for quite a while.
It was.
I saw that NASA said that the global estimate for the current rate of production of antimatter is 1 nanogram per year. Can you speak to how hard was it to make antimatter? And also, you did mention in a video that, if matter and antimatter meet, they produce a lot of energy.
Mhm.
I think 20 grams of antimatter is equivalent to a 1 megaton nuclear warhead in terms of explosive energy. Yeah, so all of those questions together. So how hard is it to produce antimatter?
It's freaking hard. Okay. All right. So here's the deal. So at the time, until 2011, Fermilab was the most powerful anti-proton production facility on the planet. Every 2.3 seconds, we would smash 10 to the 13 protons into a target, and we would get out 10 to the 8th antiprotons. So basically, in order to get a single antiproton, we needed to smash 100,000 protons into material. So every 2.3 seconds, we would get of order 10 to the 8th antiprotons. And what we would do is we would collect them over the course of 12 hours or so. And we would get, in the end, we would have to collect them and cool them down and so forth, of order 10 to the 12th antiprotons every 12 to 24 hours. So 10 to the 12th sounds like a lot. It really does. That is a trillion. But you need to remember that a gram of antimatter is 10 to the 23 antiprotons. So that means over the course of a day, we were able to create something like 100 billionth of a gram. And so if we did that for a year, then that would be about a nanogram. So about a nanogram a year, give or take. That's a reasonable estimate. So a nanogram, 1 billionth of a gram. So that means at that rate, with that facility, it would take 1 billion years running with very little downtime to make a single gram of antimatter. If you combine 1 gram of antimatter and 1 gram of matter together, the energy release is equivalent to the combined Hiroshima and Nagasaki explosions. So that tells you if you wanted a megaton, you need about 25 times more. So you would have to run for 25 billion years to get a megaton of explosive power.
Let me lay it all out because I think it's pretty interesting, actually. This is a NASA estimate of how much it costs to produce antimatter. So looking at all the costs of the accelerator, everything combined together, to do enough for a 1 megaton antimatter bomb, if such a thing it would be even possible, on the order of 25 grams, like we mentioned, will cost about, based on the NASA estimate, $1.5 quadrillion. By the way, NASA wasn't talking about a bomb. It's just me adding. NASA was talking about the estimate, the cost of $62 to $63 trillion per gram of antihydrogen, actually, is what they're referring to. So compared, I was looking at estimates, the current best estimates, how much it takes to produce a 1 megaton nuclear warhead. Everything combined is about $10 to $50 million in the United States. So you're talking about difference in terms of a weapon with equal power, $50 million versus $1.5 quadrillion. To me, what's interesting, weapons is just one indication of this. One other possibility, and NASA also writes about this, is the use of antimatter in propulsion systems.
Right.
Just like you can use nuclear fission and maybe even nuclear fusion down the line. in propulsion systems, I saw that 1 gram can help get us to Alpha Centauri star system if we can get to 0.2 times the speed of light in 20 years, meaning it would take us 20 years to get to Alpha Centauri. Is any of this a possible future, the use of antimatter for generation of energy? Because we should mention that it's extremely compact. It has the obvious downsides that it's extremely costly to produce. We don't know how to do that kind of scale.
Right.
The upside is it's compact.
It's very powerful. So the short answer is it is not a physics problem. It's an engineering problem. So I have people for that. Okay. Okay. But no.
Yeah.
The truth is that antimatter, if you are able to assemble it and store it, sure, it would be able to take that antimatter, heat up matter, and shoot it out the back of a rocket, and it would, do what rockets do. It would make us go quick, and that would be fine.
And we should mention the thing that you just mentioned is correct. One of the hugest challenges is the containment.
Oh,
because
100%. Yeah.
antimatter, when it comes in contact with matter,
Right.
is a problem.
Right. So if you were unable to contain your trip to Alpha Centauri for even a millionth of a second, boom, and that would not be good.
Yeah.
It reminds me of the Star Trek where Scotty's saying, "Captain, the antimatter pods are about, look, we're losing containment. It's going to blow." And that's exactly what would happen. So the short answer is yes, antimatter, as in principle, we could make and use as a source of energy, but there are probably far less expensive sources of energy. It depends on what you need to do. The Voyager probes are still chugging along with plutonium now. They're running out of energy at this point, but we could, presumably do a somewhat better job if we needed to. So I like the idea of antimatter, but the reality is the danger, not the obvious danger of weapons, but the danger of if you wanted to be in a ship run by antimatter, if it ever got loose, well, you would never know it. That would be that.
The reason I find this kind of inspiring is antimatter is in the space of physics that has a lot of mysteries. There's a lot of exploration to be done. And so this kind of connection to energy means that if we have a bunch of breakthroughs on the antimatter side, that might lead to a better propulsion system, better energy generation systems.
In principle.
There's some combination of engineering here, but there's some combination of understanding the fundamental physics.
I mean, we know how to do this. We know you take energy, you make antimatter. You have to contain it, you have to store it, you have to do all the hard things. But I would be shocked if there was some new addition to the theory that made antimatter production easier.
Interesting. So we know how to produce antimatter with accelerators. You're saying there's not breakthroughs in physics that could lead to different mechanisms for the generation of antimatter.
You have to concentrate energy. That's it. If there's another way to concentrate energy, that would work too.
And our best knowledge of how to concentrate energy is the accelerator.
And remember, we're talking concentrating it into volumes the size of a proton. I mean, if you concentrate it to the size of your thumb, well, then, it's really the density that matters, the local density. And so when you smash two protons together, all of that's occurring in a tiny, tiny volume. So it's the local density of energy that matters. If you had a lot of energy in a thimble or something, it's probably not dense enough. It really has to be in close proximity for that to happen. And then when it does, it's okay. So if there's another way, we know how to do it to make that density thing with accelerators. If someone has a bright idea on how to make highly dense energy, then making antimatter is a piece of cake. But that's the crux, concentrated energy.
Yeah, and how to do so in a cost-efficient manner, not trillions of dollars.
Well, yeah.
So one of the big mysteries with antimatter is the bigger why. Where is the antimatter that should kind of be there if the whole idea is that anytime you generate matter, you generate the same amount of antimatter? And yet when we look out into the observable universe, it seems like there's not antimatter for the most part there.
Correct.
So what do we understand about this mystery? What are the possible explanations as to why?
So there's this thing called baryogenesis. And as you say, so reiterating a little bit what you just said, these are both Einstein things. Einstein says that when you take energy, you make matter and antimatter in equal quantities. And Einstein says after the Big Bang, there was a lot of energy in the universe, which should have made matter and antimatter.
Mm-hmm.
We only see matter. Where'd the antimatter go? And the answer is we don't know. However, there are some ideas, and there's a lot of thinking on it. And in fact, Fermi is doing an experiment right now with neutrinos, trying to better understand what it was that made the matter and antimatter not be the same. Now, we do have a measurement of how much different it should be, and it's kind of neat. We can do this by counting the number of protons in the universe, just looking at galaxies and so forth. And then we can look at the cosmic microwave background, which is sort of the aftermath of the Big Bang, and we can count the number of photons from the cosmic microwave background. And with a little bit of math, what we can do is we can then say that somehow in the early universe, something made a very, very tiny asymmetry, so that for every billion with a B, antimatter particles that existed in the universe, there were 1,000,000,001 matter particles.
Mm-hmm.
The billions canceled, annihilated, destroyed each other, and that extra one that's left over is us.
Mm-hmm.
And so what physics mechanism made that ever so slight asymmetry is not understood. There are some thoughts. One thought is that, well, it's just how it was. When the universe was formed, there was an asymmetry. It was not made by matter and antimatter. Another possibility is there are various numbers of theories all under the word baryogenesis. Baryo coming from word baryon, which basically means protons, and genesis meaning the creation of. And we'd say that simply because the protons are the heaviest particles. And so baryogenesis is just the creation of matter. And there are just a number of theories in quantum mechanics that say that matter and antimatter can oscillate back and forth into one another, and there is a slight asymmetry in how that happens. And we know that this is true to a degree. We've measured it in the 1960s with a different form of matter. I mean, not protons, but a type of ephemeral matter that only exists in particle accelerators. And so we know that there is a slight difference between matter and antimatter, but it's not enough. It doesn't explain that. We're not sure. So at Fermilab, we have this idea which kind of turns things on its head, and it's not baryogenesis, it's leptogenesis. So leptons are the electrons. And because Fermilab is currently the world's most powerful neutrino accelerator, and neutrinos are leptons, there is this idea. Now, leptogenesis is incredibly complicated, but the idea is that it is possible. We know that neutrinos actually change their identity. There are 3 different types of neutrinos, like, cats and jaguars and tigers. And if you have a beam of just cats, if you go along a little while, you find there's cats and jaguars and then tigers, and then they'll be back to all cats again. And so this oscillation thing is called neutrino oscillation. We've known it's been true since 1998. And what we are studying is we're going to make a beam of neutrinos and another beam of antimatter neutrinos, and we're going to study the oscillation behavior of the two of them. And it is possible, it is unlikely, but it is possible that the two of them will oscillate at slightly different rates.
Mm-hmm.
And if the neutrinos oscillate at slightly different rates, then that, along with several other highly improbable things, can tie together and might explain why there is more matter in the universe. So if I was going to bet the farm, I'll bet that they oscillate at the same rate. but I don't know, and you don't know till you do the measurement, so that's what we're doing. There are some other experiments trying to measure it right now, so there's a big race between the Fermilab group and another group in Japan to see who gets there first and make this measurement, and we will find out. If it turns out, though, that there is a difference in this oscillation rate between matter and antimatter, it will be a huge clue in this very, very difficult puzzle. I wish I could tell you I knew what the answer is, but literally nobody knows. I mean, and that's the thing of being a research scientist like me, is if you're not confused, you're not doing your job.
So there is this desperate, or not desperate, exciting search for this tiny asymmetry.
Yes.
It's so crazy to think that everything we see around us is a result of this tiny asymmetry, that there was this gigantic annihilation of matter and antimatter in the
Yes.
early universe. And this is just some little accident.
Yeah.
Yeah,
Yeah. That's
it's a
crazy.
happy accident.
That is just, I mean, it's totally crazy.